Among the second period elements, the actual ionization enthalpies are in the order. Explain why. Beryllium has higher delta H ionization than boron, etc., etc. Now, this is an order of ionization energy when we move across the period in second period. Okay, and first let us graphically draw this, and let's also explore why is this the order, because that exactly is the question. First part is this, and the second part says why is it that oxygen has it lower than nitrogen as well as fluorine. Let's take a look. I think this has to do with electronic configurations. First of all, you have to appreciate that on moving across the period from left to right, size decreases. As size decreases and nuclear charge increases, attraction because of nucleus is increasing across the period, so ionization energy is expected to increase because you are pulling away the electron against the electrostatic attraction. So if there are more number of protons in the nucleus, they are attracting more strongly, so it is very much expected that ionization energy should increase, and it does. But does it increase very regularly? No. There are slight differences, like this is the trend. Let me draw this for you. If you take lithium, fine, and beryllium goes up. Interestingly, boron doesn't go up, it comes down. But please remember, when it comes down, it does not fall below lithium, it is slightly lesser. And then you find you have carbon. Okay. Then after carbon, you have nitrogen. After carbon, you have nitrogen. Very good. And then oxygen comes down. How strange. Slightly, not much. And then you have fluorine, which is very high. And of course, neon is a noble gas, so it just goes mad. Very, very high. This is typically the graph for ionization energy. And I have been asked to explain these two dips. Why a dip at boron and why a dip at oxygen. Actually, if you look carefully, you can relate this with their electronic configuration. Beryllium, now this is, lithium is 2s1, 2s2, this is 2s2, 2p1. So beryllium has higher delta H ionization than boron. Why? It is because in case of beryllium, the electrons are being removed, the electron is being removed from s subshell. S subshell is closer to the nucleus, and the electron in S subshell is held more tightly. It's attracted more strongly by the nucleus as compared to the p electron, which is going to be removed in the case of boron. Wow. S for strength. So since in the case of beryllium, 2s electron is being removed, which is more difficult, and in case of boron, 2p electron is being removed, which is easier. You find that ionization energy of boron slightly dips, and it is lesser than that of beryllium slightly. This was the explanation which was expected here. And then we have the next question also. O is lesser than nitrogen and fluorine. Why is it? See, across the period, ionization energy anyway increases because of increase in nuclear charge. So fluorine was very much expected to be more anyways. We are worried about why oxygen has lower delta H ionization than nitrogen and fluorine. How do we explain that? That can be explained by the extra stability of half-filled p orbitals. What? Yes. Nitrogen has electronic configuration 2s2, 2p3, while oxygen has electronic configuration 2s2, 2p4. Now, as nitrogen undergoes oxidation, what you can say is ionization, like this. Then 2s2, 2p3, you are removing an electron from 2p orbital and you're just putting it like this. Half-filled p orbitals have extra stability, and ionization of nitrogen means you are destroying the extra stability of half-filled p orbitals, and that is why they need an energy which is slightly more than the regular energy they would be expected to need. Okay, and in case you're looking at oxygen, opposite is true. Why? Oxygen has electronic configuration 2s2, 2p4. Now, does this oxygen possess extra stability initially? No. But once you ionize, after ionization, you have taken away one electron, oxygen is expected to be not to be very happy, yes. But there is some trace of happiness. In what sense? Original O did not possess extra stability of half-filled p orbitals, but O plus indeed does have extra stability of half-filled p orbitals. So that is why taking away electron from oxygen makes it slightly, more comfortable, more easy, because okay, fine, electron is gone, but at least I have extra stability. In this case, nitrogen, it is worst. Not only have you taken electron away, you have also destroyed the extra stability. So that makes it more difficult for nitrogen. So it's a little more than expected, and that makes it somewhat easier for oxygen. So it is a little less than expected, and that is why O has a slightly lesser ionization energy than nitrogen. Can we compare O and F? Yes, we can. How shall we compare? Well, across the period, as we move from O to F, nuclear charge increases. Because of greater nuclear attraction, we find that more energy would be required for removal of electron. So ionization energy anyway is expected to increase from O to F. So that's quite okay. And that is the explanation why O is lesser than both N as well as F.